All right. Good morning. Let's start. Do you have any questions? Okay. Yep. Good morning. All right. So let's begin where we. Yeah, sure. Yep. All right. So let's begin where we left off from last time. So basically, we start to introduce the Poisson model. Okay. So let me say, so Black-Scholes model with jump component. And so roughly speaking, right, ignoring all the martingale property, then we have a physical model that looks like this. Okay. So here we introduce one extra source of noise. So two sources of noise. Where Wt is the Brownian motion and Nt is the Poisson process. So to remind you, the Poisson process has the following properties. It starts at 0, has independent increment, and identically distributed increment. We know what that means by now. And to completely specify the picture, we need, I guess here's, we need a Poisson lambda process. Okay, so we need to specify the rate. So unlike the Brownian motion, where the Brownian motion does not depend on any parameter, the Poisson process itself requires a rate to completely specify it. Okay. So one thing to note is that these two properties are exactly the same as Brownian motion. So in many ways, probabilistically, the Poisson process behaves like a Brownian motion. Okay. So, for example, when you want to compute certain things like conditional expectation, right, for nt conditional on s, for s less than t, you would do exactly what we did before with the Brownian motion. In other words, you would, introduce the increment, the future increment, right, and then keeping the present. And so, and then you would use the independence to drop the increment, to drop the conditional expectation, drop the conditional, for example, and then you'll get this to be right. So the probabilistic calculations that involves Poisson process should follow exactly the same procedure as you would do with the Brownian motion. The only difference, of course, is when you start to compute, right, the explicit structure, the explicit distribution, then instead of using normal, right, you use the Poisson process. But anything else would be similar. On the other hand, right, in terms of calculus or pathwise, right, the Poisson process is very different from the Brownian motion, right? Actually, you can say it's exactly the opposite of the Brownian motion. So in other words, the Brownian motion itself, right, is continuous, but nowhere differentiable in T. The Poisson process, on the other hand, right, has jump, right? This continuity, but otherwise it would just be differentiable because it's just constant, right? But otherwise just constant. So in other words, while this guy changes all the time because it's nowhere differentiable, the Poisson process rarely changes, right? Rarely changes. But when it changes in a discontinuous way. So what that means, right, is that in terms of calculus, the calculus, right, I mean in quote, because actually is has jump discontinuity, so it's not really calculus, but we can just say, right, the way we handle, right, the path property of the Poisson process for Poisson process is very different, right, from the Brownian motion, from the Ito calculus. All right. So I want to point out these two observations. So you know that if we have to do with the probability, then you just rely on your intuition about the Brownian motion and work out the details. But if the new thing, right, to understand this new model right here, the new thing is to understand what we mean when we do DNT like this. Okay. So that, well, one of the new things. So that's the calculus part. Okay. That's the calculus part. How to add with DNT, how to work with DNT is the question. So this is exactly how to understand and work with DNT. Okay. So let me tell you right away, right? So the fundamental things is how to define, let's say, the integral from 0 to t of this. Okay, where f is any function in time. Okay, so what happens, you know, is this. So here's a path, right? Suppose here's t. So there are two things. First, your n starts at 0, right? And then it jumps, and then it jumps like that, for example. So suppose that it jumped 3 times, right? So here's tau 1, tau 2, tau 3. And of course, we denote, right, the value like this. So it, right, so this is nt. Okay, so this is right continuous. With left limit. Okay. So of course you can still draw a graph for f. But f can be whatever you want, you know. Suppose this is f. Okay. So our goal is to combine these two guys together into an integral. All right. Our goal is to combine these two together into an integral. Actually, if you understand what we did with the bound motion, d and dwt, then the intuition for how to handle this guy is similar. dn represents a change, right, in the path of n. So let me ask you this, for example. So here's a general picture for any t, right? Suppose that t is less than tau 1. What should be the integral like this? If I restrict the t to be less than tau 1, right? So before tau 1, before the first jump of the Poisson, what should this be? Any intuition on this? No, no, no. Because actually, right, think about what you say. The object you're giving me does not represent what I'm asking. Because when you say this, right, first of all, what object we're looking for here? We're looking for a number that depends on t. What you're giving me here is a differential, right? They're completely different objects. Maybe you have in mind something like this, but I'm not asking for the differential of this integral. Does that make sense? I'm not asking for how this integral changes. I'm asking for the value of this integral, meaning it does what it does. When I add, right, the function with the change of the Poisson process for up to any time before tau 1, what is the value, right? So FSDS is not the answer. It's not the appropriate answer. All right. So again, right, what does DNS mean? DNS means the change of the Poisson process, right? At every time, just think about how you simulate the integral against the Brown motion before. You do dw, right? And then you add it up. Same thing here then, right? You would do dn and you add it up. But up to time tau 1, what is dn? Up to time tau 1, what is dn? Correct. So the whole answer is 0. You understand? Because basically you're just integrating against a constant. I mean, this one, so dn is equal to 0, right? So the whole integral is 0. Is that okay? So then here's a catch. What about the integral up to tau 1 of this? What would that be? Is that still 0? Not quite. Not quite. What's the difference? Up to tau 1, right? There's no change in the Poisson. But at tau 1, is there any change?
Oh, yes, because it just like jumps from 0 to that value.
which is
So
1, right?
yeah.
So I hope it's no surprise that it will be f of tau 1 times 1. I mean, we can ignore that 1, right? But exactly it will be f tau 1 times 1.
Mm-hmm.
Is that clear? So in general, right, like what Don said, if the jump is not 1, it will be f tau 1 times delta n at tau 1, whatever that is, right? Where by delta n tau 1, we mean the value minus its left limit, which is a jump size. Are we okay with all of these? But of course, right here, the answer is just f of tau 1 because the jump size is 1. Okay, let's continue. What if we have now our t is between tau 1 and tau 2? What is the integral then? What is the integral? Very good. Exactly. It's just f of tau 1, right? Very good. Exactly why? Because it picks up this value right here when it goes across tau 1, and then it just stays there, right? It just stays there because there's no more jump. Very good. Are we okay with this? And then, of course, right, if you cross tau 2, then what is this integral? I hope it's clear that's f tau 1 plus f tau 2. Yes. So in general, right, now, as we mentioned last time, the fact that the Poisson process jumps by 1 is just a convenient value, right? We can change it later. So let me denote this, okay? Let J as be a pure jump process. Maybe JT, right? Doesn't matter. So by a pure jump process, I mean something like a Poisson process, except we don't say anything about the distribution of this process. It's just a more of a path property. What it means is it can start anywhere, right? It can start anywhere. Let's just say it starts at 0 to make it easy. Then it jumps, then it jumps, then it jumps. Is that okay? So basically, by a pure jump process, I mean anything that stays constant in between the jumps and jump size arbitrary, positive, negative, whatever. Okay. Then I will be able to define the integral against this pure jump process, right? What would be? It will be the sum of f, right, of tau I times delta j at tau I, sum over all I, such that tau I is less than or equal to t. Are we okay? Are we okay with this right here? So this is the start of the calculus. This is like defining the Ito integral, right? Except that this is the integral against a pure jump process. It's very intuitive, actually, right? No need for fancy math, but you want to understand what it means by the change, and that's all there is. Okay here? Any question? All right. So let me observe, right? It probably is not super important that this right here is also a pure jump process. So you can even give it a name. You can call it XT or something, or QT, right? That jumps exactly at the same time as J. Is that okay? So in other words, right, if you have a pure jump process, you can integrate against it. What you get is just another pure jump process. Of course, right, what changes what? What change is a jump size, right? Look at here. What we're saying is actually, you see, if you, right here, if you integrate against the Poisson process, what you get is a pure jump process where the jump size will be, for this case, the value of the function, right, at the jump point. Is that okay? So the jump size for this new process right here is the value of f at those points. So if somehow f is negative at some of these points, right? If somehow f is negative at some of these points, then this new integral will be negative on the first jump, right? And positive on the second jump, for example. Jump size. Are we good? All right. So using this knowledge, okay, so if you have any question, ask me, all right? Because we're going to build on this knowledge to solve our equation. So building on this knowledge, right? Let's revisit our stock model. You know what? Okay, so let me write down the whole thing. So let us investigate this, right? One by one. So first, let us make it simple by ignoring mu and sigma. Okay, let's just purely investigate on this. So in other words, let's look at this. All right. Well, so first of all, you should recognize that this is an equation, right? This is an, you can call it a differential equation, if you will. It's just not differential in dt, right? This is an equation, right? For S, right? So suppose that S0 is given. The obvious question is we want to solve for ST, right? So this is our stock model. This is our stock model with jump. Okay. If it's given like this, what is our stock price? Or, right, if you will, if you remember, basically, right, this is the model for our return, right? But it's basically a stock that's pure jump. So, right, you imagine you have a process somehow that has this pure jump, probably like, like interest rate or something, pure jump. You can still define the return, right? A percentage return like this. So, right, but if you have a pure jump process like this, right? What is the value? Okay, what is the value of the stock price? Well, so I guess I give the secret away a little bit. That if you look at this, you see this equation tells you that the stock price in this model is also a pure jump process, right? So here in this model, ignoring these two components, then this describes a pure jump process. Is that okay? I mean, it's a very simple observation, but it's super important. So I hope you understand that, right? In other words, here ST cannot do anything besides jumping, right? So maybe let me, for the benefit of the audience, right? Let's draw again. Let's suppose that we have, this is NT. Okay, so this is NT. Okay, so tau 1, tau 2, tau 3. So then what I say is that my stock must follow the same way. In other words, if this is the model for my stock must be starting here. Whoops, too far, right? Then it will jump, then it will jump, then it will jump. So in other words, if the stock model is like this, my stock will be pure jump. It will jump exactly at the same point as the Poisson. The difference though is a jump size. Okay, how much are these jump size? Is that okay? What are the jump sizes? How do we decide this? So by the way, let me pause here and ask, right? Maybe I'm moving too fast. Is it clear that from 0 to tau 1, the stock price cannot have any change? Because, right, when writing this, you're saying, well, because DNT, right, DNT is 0, right? So, and then of course here, thank you, Kashif, right? The Poisson jump 1, so there's some jump, right? And then the Poisson doesn't change again, so the stock doesn't change, right? And so on and so forth, all right? So let me ask, right? So the only question left is the jump size. So ST, right, starts out at 0, right? Sorry, start out at S0, right? Whatever that is, $100. It will continue to be S0, right, until tau 1. All right, at tau 1, there's a jump, right? So the question is, what is S tau 1? Okay, because that's the only question left. After we figure that out, then we will know the whole story about the stock price. Can anyone tell me what do you think the new stock price is after the jump? Based on this. So let's see, right? The recipe is completely given here. Remember, D represents the change, okay? But what is the change of the stock price at tau 1? Well, the change at tau 1 will simply be this. Almost, Sherry, almost, all right? Almost, because you're not, very good guess. You just kind of didn't really look into the formula. Oh, no, it's not about late or not late. It's a new thing. So that's fine. But yeah, it will be, right, almost your guess, but it'll be gamma S tau 1 minus times delta N tau 1. Is that okay? That's writing this out like that. This is analyzing, right, this formula at tau 1. Okay. Now, let's go with it, right? So what is S tau 1 minus? What's the value of the stock just right before the jump? It will be S0. Correct. So you get S tau 1 is, right, S0 times 1 plus gamma. Is that okay? But of course, what is delta N tau 1? Because the Poisson only jump 1 unit at a time, we got this to be 1 plus gamma. So Sherry, if you were talking about the jump size, then yes, it's exactly S0 times gamma. But the new value, right, because you need to add the old value, will be S0 times 1 plus gamma. Yeah. Are we okay? And so, right, so we know what the value here is then, right? We know what this value is. Then you see then, right, then the story just continues. Just figure out our next value. So what is S tau 2 then? Right, and I hope it's clear, right? Then it stays the same in between, and then it jumps, right? What's S tau 2 then? I hope it's clear that it's going to be S0 times 1 plus gamma squared. Correct. Right, so it's actually a very easy model, right? So ST in general is going to be S0, right, times 1 plus gamma raised to what? Tell me. If you can guess what the question mark here, then you would understand completely what everything we discussed so far. So in this pure jump model, right, from our analysis, we'll get this. What is this question mark? No. T can be any value, right? Like square root of 2. You see clearly we want an integer here, right? So it's not T. All right, let's go back. Why do we put 1 here? Why is this 1 here? And why is it 2 here? Anyone see something? What is this question mark? Well, I hope it's not too mysterious, is NT. Does that make sense? Take a look, right? Before this, NT is go to 0. So there's no jump. That's just S0. After that, right? So basically, you see, you are really just counting how many jumps. You're only counting how many jumps the NT has made so far. And that's why, right? If you have taken any courses like, you know, in stochastic process before, NT is also called a counting process. And I hope you know why. I don't want to introduce this this name because, you know, we will quickly move away from Poisson process. But you see why, right? It just keep count on how many points it has jumped so far. So that's why, right? Here is quite neat that we can put that. Yeah. Any question? All right. So now, so for simplicity, right? For simplicity, we ignore these two parts and we just keep this. So now let's put this back in, right? Let's put this back in. So let's look at the complete. Black-Scholes model. Okay. Then, all right. So what happens? What happens is, you see, let's investigate the picture again, right? So you have the NT. Okay. So now we have our stock. It starts at S0, right? And here's tau 1. Now, under this model, where I let mu and sigma, right, come back in full force, does S stays constant between 0 and tau 1? Does a stock price stays constant between 0 and tau 1? No, right? Exactly, because it has the dt and dwt, right? So here's the NT picture. But of course, meanwhile, if you want, right, if you want to be super detailed, the WT has already been moving, right? This is W up to, right, tau 1, tau 2, tau 3. W has been moving. And if you really want, right, T has also been moving, right? So you see, like, these three guys together, right, make up your change in the stock. So clearly, right, the stock has also been moving. So it moves, whatever, right? And but then at tau 1, right, something special happens. Well, what? At tau 1, the Poisson process jumps. So then the stock also jumps there, right? And then it moves, and then it jumps. Sorry, like this, and then move. Is that okay? So in between, right, it moves as if there's no in between the taus. Then what you have is this. So that's just the old Black-Scholes model. It just moves like a Black-Scholes model. At the tau I, what happens? At the tau I, then, right, at a single point, because these guys are both continuous, at a single point, their change is 0, right? There's no change at that single point. But of course, at tau I, right, it still pick up a change. That change comes from the Poisson. So in other words, at tau I, it still picks up a change. And the change will make it jump by this much. So that exactly is the jump size, right? That's the jump size. But you see here, right? The jump size depends on the previous value, right? The Poisson process has constant jump size. When you feed, because, right, but it's very obvious. It's just right here. You say that the jump of the stock depends on its previous value. That's exactly what you want in this model. And here we just spell that out. Okay. So you see that why we have to be super careful to plug the gamma to be a small value. Because if you ignore the gamma, right, or sorry, not ignore the gamma. If you don't have a gamma, that means you have a 1, right? Actually, it's not ignore the gamma doesn't mean that you have no gamma. If gamma equals to 1, then you're saying that at every jump price, at every jump point, the stock doubles in price. And that will make the stock explode in no time, right? But otherwise, right, the understanding of the model is very much the same as what we did before, except that before, right, we have a very simple model because there's no change in between. Here we have a slightly more complex model with change in between. Okay. But that's no problem. I still can put together these two observations, okay, to give me a formula for the stock price in this case. Does anyone want to guess what the formula for the stock price is in this case? So let me give you a hint, right? So when gamma equal to 0, meaning when there's no jump, then that's the old Black-Scholes model, for example. Then we got something like this, right? ST is S0 e to the mu minus 1/2 sigma squared times T plus sigma WT, right? When mu and sigma are 0, so when we turn off. And by the way, right, we can call this the continuous part, right? The continuous component of the stock. These are continuous component. These are the pure jump component, right? The stock can be decomposed into a continuous component and a pure jump component, right? So when we have no jump, then this is the continuous part. When we turn off the continuous part, then we got something like this, right? So what if we have both together? What if we have both together? Then what is my stock? What is my formula? Add. Is it adding these two? You're almost there. It's multiply these two, but not quite multiply. Correct. Correct, exactly. Right? Do you see why? It's actually comes from these two observations. Because in between, I move like this, right? So I would follow this up to here, follow this. Then at here, what do I do? At here, I just pick up a 1 plus gamma. So I multiply again 1 plus gamma. Then what do I do? Then I start with a new value. Then I just go on my happy way with this formula again. So that's where it is. And then I'll pick up another jump. You see, it's a very multiplicative structure. It's not a sum structure. The change, right? The change may seem like a sum, but don't forget, right? That sum is a little bit. That sum is just meaning adding the noise sum. The structure is still multiplicative because of this. All right. So that's your explicit formula. Question? Are we okay here? Oh, excellent. Very good. Yes, in some way, absolutely. We'll talk about that. Yes, but what you're very close to the truth. We can add 2 Poisson process, but we can do better. We can even be a little bit more sophisticated, but you're almost there. Yes. Mm-hmm. Any question about solving this before we continue? Right? It's very important that you understand the calculus. My point is, right, the calculus is actually quite intuitive. It's the old calculus plus what happens at a jump. That's all there is. So now let me decorate this a little bit, right? If you want just one single exponential structure, you can do this. Okay. So for me, this is pure decoration, right? Basically, you want to put everything on exponential, so you do this. But I guess here is much easier to understand because of our previous analysis, right? Where it comes from. This looks a little bit mysterious, but who knows? If you just really want to be kind of put everything under the one single exponential, you can do that. All right, so that takes care of the calculus a little bit. Now let's go back to the martingale structure, right, and the pricing formula. And so, I mean, I hope you see that what we're doing, right, is quite similar to what we did before. And then this is how you think about any pricing structure, any model, right? In case you have to deal with new models later on your own, not in this class, right? So you see the program, right? Is to understand the calculus. What that is, how does it move in time? The second is the probability. How does it move in terms of distribution? then the martingale structure. Because for pricing, right, what you need is you need e to the minus RT ST to be a P tilde martingale. And then for pricing. And I mean, you can throw in a fifth here, PDE. Okay. But you see that with the Brine motion, we did exactly these things. Maybe not in the same order. Sometimes I jump forward, sometimes I jump backward, to kind of make connections. But these 5 components makes up the understanding of pricing of any model. Okay, any product. You could look at like bond pricing or foreign exchange pricing in the same way. Except of course, right, whatever that is has to be a martingale, you have to look into it. But yeah, so if you keep this structure in mind and like kind of see how the presentation goes, you know exactly what is being discussed at which time. So we just finished with the calculus. The probability I kind of wave hand over for the Poisson process. The reason is I say it's very similar to the Brine motion, right, in terms of independent increments account thing. So that's why now we move to the martingale structure. Okay. So the martingale structure. And by the way, right, I mean, I guess that Professor Larson puts a lot of attention to the martingale education for you guys. I hope, right? I mean, if I guess correctly. And the reason, right, I'm not sure if you understand or appreciate it, why so much emphasis on martingale. The reason is martingale structure is the structure underlying the language of pricing that we do, right? Whatever model you do is always there. Whether you want to call it out explicitly or not, there's a martingale structure behind. And of course, like the name sounds scary, but the moment you introduce this concept, everything actually simplifies. Everything becomes simpler, all right? So except that you just kind of need to know what the concept is. And so why martingale structure? Again, right, the martingale structure comes because of market condition, all right? The martingale structure comes from the market condition that the price, right, you have 2 time moment. The correspondence between whatever you're looking to price must be this. In other words, a future process S big T must have current value S little t. I mean, right, that's like a truism that everyone would say. There's nothing there. But translating to the language of math is a substantial relation because it tells you that this must hold. Right? Again, you see, connecting these 2 values comes down to this. And of course, if you factor the e to RT over here, then you got okay. And you see why, right? That the discounted stock price is a risk neutral martingale because of exactly this, and this comes on the market. All right. And so you see that when it comes to pricing, it's the same thing, because now you say, well, this doesn't just hold for stock, it holds for anything depending on this stock. So in other words, if you have a derivative, it must hold in the same way. So, right, what you're saying is you just extend this picture to the derivative, to any V, right? Any V that has a relation to the stock. But again, I think that's really a truism that no one would question, because if you have a value process that's being traded, of course, the fair value of the future is current value. So, but then again, right, you see this translates to that. And this is why I say, right, that the martingale structure is the structure underlying all the pricing that we do. But you see so that's highlighting martingale. But you see why, right, that the move is not trivial mathematically, because look at this, right? Look at this guy right here. Is this necessarily a martingale? In other words, right, when you discount this, is it a martingale? And the answer is no, it's not. Okay. If you just write down a model, right, the lesson from Black-Scholes is that if you just write down a model, it's discounting it is not a martingale, right? If you're just given a model, then the discounted is not, okay, necessarily a martingale. All right. And so therefore that prompts you to ask, okay, what do I need to turn into a martingale, right? So actually that prompts you to ask two questions, like two directions, right? Two types of questions. What characterizes a martingale? Okay, because you definitely do not want to, I know that, like, you know, this is the traditional definition of martingale, right? Conditional expectation of the future value is equal to the present value. That's how you think about martingale, right? Go back. But in terms of like mathematics, computing conditional expectation may not be the best thing to do every time, right? Considering the structure of the object you're looking at, right? I don't think anyone would enjoy feeding this whole thing into a conditional expectation machine and try to calculate it. We can, it's not that hard, but right, the complexity just build up if you don't try to keep track of things. So is there some other way to characterize a martingale so that when we glance at that, we'll say, yeah, of course, that's a martingale, no need, right? For example, like, why do I know, for example, if I have something like this, then I have a martingale right away, right? This is the classical Black-Scholes, right? But this is the risk neutral prime motion. This is R, right? Then no, I have a martingale right away. What gives it, right? And so that's the first direction, right? The second direction is how to convert, right, into a martingale. So I make this question a little bit vague, but what I mean is this, right? So clearly this is not a martingale, right? How do I, you know, do something to make it to a martingale? And of course, the answer here is a change of measure approach, right? Change of measure, change of probability. Okay, and I hope, right, this change of measure is probably one of the most mysterious aspects of pricing. All right, so at first you just learn to do it. All right, but I hope that you see it's not really too much of a magic. First of all, when you do change of measure, you do not change the stock price itself, Remember how we add and subtract something, and we introduce a market price of risk, and we are very careful to to specify how the new brand motion is related to the old one, right? Those are not pedantic considerations, right? A little bit pedantic, but the point is that we want to emphasize that we're not magically move the stock to a different world, like where it becomes a different stock. The process itself physically is still the same process. What we change is we change the point of view. We change the probabilistic way, right, of looking at things, right? If, in other words, if you want to look at an equivalent description is you roll a die, okay? The value 126 will not change. I'm not repainting the die. I'm just rethinking of how the probabilities of landing on each of these face is. And let's face it, right? I mean, no one knows exactly that these are 1/6 on each of the face, right? That's also in your mind. That's a model, right? When you roll a die, you say the face has probably 1/6 each. How do you know? I mean, why? Right? Maybe the face are not perfectly like cut, right? How do you know? Why is it exactly 1/6 each? So rethinking the probability on the face of the die is exactly a change of measure. So rethinking the probability, right, on this W and this N, for example, as we'll see, is a change of measure. But the way we change measure is also reasonable in this way, that if something is impossible in the original model, impossible means probability of happening is 0, then it's also impossible in our new measure. That's called equivalence, right? The measure is, the new measure is equivalent. The new measure, the new probability is equivalent to the old one. So in other words, any event that is 0 under the new one will be 0 in the old one, all right? So impossible event in the physical world is also impossible in the risk neutral world. What implication does that do? The implication is that then, if you have no arbitrage in the risk neutral world, right? No means impossible. Then you also have no arbitrage in the original world. And that's all we can, like kind of make sure of. All right. So I just want to bring a little bit of a meaning into the change of measure process for you, right? And why we do the way we do. But of course, right, for the class, we just focus on these two questions and, again, introduce more technicalities, introduce more details, right, into each of these process. All right. But because now we introduce a new model with a new component, so we need to, right, again, answer these questions fresh, how to do these things for the new object. All right. But I hope you, again, right, reappreciate the whole reason why we do these things for pricing. Any question? Okay, so let's address A first. Okay, let's address A first. So again, right, I mean, before I did not go in too much into these details because the structure is still quite easy. It's just brand motion. Now the structure gets more complex, so I need more, more concept. So the categorization of martingale in general is this. I mean, there are many ways actually, but the easiest categorization is this, that if, right, let's say you have xt is a continuous martingale, then the integral is also a martingale. Okay. So in other words, this is just saying that integrating against a continuous martingale is remains a martingale. All right. And by continuous, I mean continuous in path. All right. I mean, here, all you have to think of is prime example. Ground motion. Okay. So in other words, it's just a good old statement that integrating against a ground motion is a martingale, right? I said that before, kind of, not very much emphasizing on it. Now it becomes important, right? So the intuition is, again, right? This is the gain you'll get betting against a martingale, right? Because this is a change, and this is how much you get compound with that change. And if this change in general, right, is zero, it's fair, it doesn't move. Because if it's a martingale, then the expectation of the change is zero, right? A martingale means constant expectation. So if it's a martingale, then the expectation of the change is zero. Then overall, right, this one does not move in expectation on average. That's why it's martingale, okay? The only complication that comes in is that it can be a pure jump martingale. If it's a pure jump martingale, you have to be careful. You have to do a minus. Okay. So the difference is that if it's a continuous in path, then you integrate, you bet against this martingale, you're fine. But if it's a pure jump martingale, then you need to make sure that this guy is predictive. I'll explain. Okay. So, for example, right, what is the prime example here? Obviously, I have the Poisson process in mind. Okay. But of course, the issue is the Poisson process a martingale? Poisson process is pure jump, right? But is Poisson process a martingale? Well, let's check. Yeah, I'm guessing no, but you can have an intuition on it, right? For example, remember a martingale, right, means that something that is constant on average, right? A martingale means something that's constant on average. But suppose that you have something that's always increasing. Correct. If it's always increasing, then of course it's always increasing on average too, right? Therefore, it cannot be a martingale. That's exactly it. So to be a martingale, you must sometimes come down. If you don't come down, then you cannot be a martingale to begin with, right? So of course, right, you can also do computation. The one that I did at the beginning of class. And this, right, clearly you see is bigger than NS. Why? Because the rate is positive and this is positive, right? T is bigger than S. So yeah, that also reflects the upward moving, right? But this right here, right, actually makes it easy for you to see what is a martingale, right? This is it okay? So this is called a compensated Poisson process. Is that okay? Right? Because the Poisson process always increasing, you need to compensate, right? And you compensate exactly by what? By the trend, right? The Poisson process moves with the trend of lambda t. So you subtract the trend, is a martingale. Very easy. Any question on this? So this kind of, right? So this kind of explains in your worksheet for last Friday, all right, I give a model, and I think you see something like this. Okay, so this is a risk neutral version of the Black-Scholes model, right? So you see why? Because the drift now is R, right? This is the Newbron motion, and this is a compensated Poisson process, right? Because the compensated Poisson process is a martingale. This minus right here, keep it a martingale. This part right here keeps it a martingale. And of course, right, this is taken care of by e to minus RT. So the discounting will take care of this. So therefore, it becomes a martingale. You see? Sorry, this is not NT minus, right? NT subtract. Are we okay? And you see here, right, how the martingale structure is very helpful for us to just say there, right? And how do you apply this? This is by Ito's formula, right? By calculus, by doing the differentiating with respect to t and do the ds, right? So you get that. Any question on this? Right. So let me conclude, right? All right. So let me ask you, right? Or any question before we continue? So the new one we introduced, right, is this idea of compensated Poisson process, right? Compensated Poisson process. The tilde is because when you move to a risk neutral probability, the Poisson process may pick up a different rate. Okay, it's no longer rate lambda; it's a different rate. Just the same thing as saying that the Brownian motion changed to a different Brownian motion, right? It picks up a drift. I'll explain that, okay? But yeah, okay. But otherwise, right, the idea is a compensated Poisson process. So this is our new martingale, right? So you can think of your stock model as driven by different martingales. That's what it is. Your stock model is driven by different martingales, with the drift always being the risk-free rate, okay? Now, so let's try to see why, or try to intuitively see why, that if something is a pure jump martingale, then you need something like this for it to remain a martingale when you integrate. So in other words, right, why this won't work? Why won't this work, right? So basically, the intuition is that, right, we say this is a martingale, right? So it's just like a process that moves up and down. This represents kind of a bet, right? You're betting on the movement. We say that if the up and down somehow has zero expectation, right, the change, then no matter how much you bet, right, you cannot gain on those sequence of bets. And so you should stay a martingale. But why here, right, you're forced to somehow use the left point in the betting scheme. Does anyone have any intuition on why? Okay, so it has to do with this circle and dot that I was careful to write, right? This is exactly where it matters. So the intuition, there is some financial intuition in this kind of formulation, actually. Because when you think about it, it's pretty arbitrary on why you put the dot here and not here, right? Why not put a dot here and a circle here, right? So you understand what that means, right? That means it's left continuous with right limit, but we do right continuous with left limit, right? So in other words, we say that, right, at the jump, the new value is after a jump, not before. Okay, why is this the case? This is the case, right, to reflect, if you will, that the process itself is not predictable. But predictable here has a very precise meaning, all right, in finance, in this context. It's not like predicting like what you would think. Predictable means that if you have been observing the value so far along the time stream, can you guess what its immediate next value is? You understand? If you've been observing the value, can you guess what the next value is? Right? And here you see that you would not know up to the tau 2 minus, right? Or up to tau 1 minus, you would not know what the value of tau 1 is, because you never know if it's going to jump the next moment or not. Does that make sense? So you do not know the value of n tau 1. I hope you kind of see the intuition here, right? If I keep staying like this, right, just think about a stock movement, the stock jump, right? Up to the moment that it jumps, you never know how it would jump, right? Of course, there's some kind of cheating here because you say that the Poisson jumped by 1. So the moment you know it jumped, you know how much the value is. But just exactly the point is that you do not know when it jumps, right? Even if you have observed everything up to that moment, okay? Up to that moment, of course, not including tau 1, because at that moment you already know it jumps. But up to very close to that moment, you do not know when it jumps, okay? So because of that, right, that actually captures that our intuition that the jump is a shock, right? The jump is a shock. Because if you transfer, suppose you transfer the dot over here and put the circle here, then actually what you're saying, right, is that I know the value of the stop up to that moment. So it's predictable here, right? Up to tau 2, as long as I observe it up to tau 2 minus, I know what the value is, because the value of the stop is before the jump, not after the jump, right? And that's not the intuition that we have about stock price in general. So when you have a betting scheme against this thing, right? When you have a betting scheme against this thing, if, right, we are allowed to use, okay, something like NT as our betting scheme, in other words, you want to do something like this. I'm not saying that this will work. You need to modify a little bit. All right. So in other words, you see right here, this FS, what I was doing is I just used the Poisson process, right? Then basically, because I'm allowed to use this in my betting scheme, I have access to the future. I have access to the future. Then basically I know, right? I can anticipate what value the Poisson process will be when it jumps. Then I can anticipate this. This is similar to being able to anticipate the move. Before it happens, because you have access to the NT itself, right, in your betting scheme. So it's like peeking into the future. It's very subtle, all right? You're just peeking a little bit in the future, but because you could do that, right? It's like the moment before the jump, you can peek into it. Then this will spoil the martingale property. And that's what it is, all right? That's all the intuition I want to give you. If you want to see the precise calculation, you can see the example in Shrift. But basically, if you can somehow anticipate the future, right, the process is constructed so that it's not predictable. But somehow, if you use the process itself as a betting scheme, then you can spoil that property, right? Notice that NS minus is not equal to NS when N jumps. Okay, so the NS minus is exactly the process where it's a dot here and a circle here. You understand? NS minus is a process where you transfer the dot to the left because you take the left limit. Okay, so therefore, when forcing you to use the minus version, make sure that you don't peek into the future when you bet, and that's why it will remain a martingale. All right, and one last thing I want to say is this, right? So basically, if, right, you have a something is continuous in T, then xt minus equal to xt, right? This is clear, because if something is continuous, then the left limit is equal to itself. So in other words, if you have a continuous process, in other words, right, if your betting scheme is continuous in time, then actually this notation is not necessary, because it's continuous, then you just use whatever it is. This notation exactly is useful when you try to cheat by using something like this in your betting scheme, right? So when if xt is not left continuous, then is that okay? So the minus sign here forces you to use the left limit at every point. And so if it's not left continuous, then the values are not equal. All right. And but in the formulation of the martingale, you need to use the left point limit. And so again, right, that explains why we insist on using ST minus here, right? The value of the jump, right? The value of the stock is the value before the jump times the jump size, not after the jump. And that explains that. So you always move from left to right. You don't peek into the future when you do this. All right. Any question? So that's a bit of technicality, but it needs to be explained. Okay. All right. So next, let's talk about the change of measure. Okay, change of measure. So what do we have here, right? What do we have here? So what we start, right? We start out with the stock being in the physical model, physical world. Okay. And you want to move to something with risk neutral drift. Okay, like this. Okay, where, right, obviously two things must happen. First, W tilde, right, is a P tilde running motion. And NT is a P tilde Poisson lambda tilde process. Okay, so two things. So of course, the question is how to define P tilde. Okay, how to define P tilde. And so obviously from the experience that we had before, so clearly, right, the way you define P tilde as is via this formulation. Expectation, right, of any random variable under the new probability is expectation under the old one times some change of measure kernel. So of course, then the question is, what is ZT, right? What is the change of measure kernel? And then this actually, right, reflects back on what do we want? What do we want? We want this, right? So then the question is, right, this depends on what we want. It depends on what we want to happen under P tilde. Namely, what do we want to happen? We want that the W tilde is a P tilde Brownian motion. Yes, Don, right? But wanting ZT to be equal to 1 is very simple, right? There are a million things that can happen that can satisfy that, right? You want to be very specific, right, on this. ZT equals to 1, that expectation, right? So what you say is the minimal, right? Minimally. You want that, but more, right? Because that just categorizes any change. This is some very specific change you want. You want W tilde to be a P tilde Brownian motion, and you want NT to have a different drift, right? And so that's why you want this ZT must be more specific, right? So now actually let me go back to here, right, and kind of maybe try to connect again, right? Do pay attention that the point is these guys are the same, okay? These are the same. It's not a different stock, it's the same stock. So somehow this must be relatable to this, and this must be relatable to this, right? So what is the connection? What is the connection? Right? So let's go back. The old one. Right? What is the connection here? Well, obviously, first off, we have this, right? And the connection is yes. So this is called the market price of risk equation. Okay, market price of risk equation, because right, this is the Sharpe ratio, the price of risk, right, for the stock. This is the price of risk, market price of risk for the stock, right? Market price of risk equation. Is that okay? So in our new equation, right, in our new model, right, what is the connection? What is the connection? Well, so let's write it down, right? So DST is the old model, right? Is the hardest thing is to write this down again and again and again. It just takes too much time. Okay. So obviously W tilde is still WT plus theta T, right? Theta is our unknown shift. What is the market price of risk? What is the market price of risk equation? Well, you just put things together, right? You got R plus sigma times theta plus, rather minus, right? Is that okay? That's our market price of risk equation. So actually be careful here, right? In this equation, how many unknowns do we have? Correct. Two unknowns, theta and lambda tilde, right? Correct. So exactly that. You see the move to the risk neutral version picks up, right, a new drift for the Brownian motion and the new rate for the Poisson. But actually, right, you see these are actually the same thing, because the Poisson process, remember, has some kind of drift, right, by itself. It drifts up, right, at what rate? At rate lambda. So in that sense, actually, it's just a new compensation, a new drift, right? So actually, both the Brownian motion has zero drift before. Now you add some drift, but it's just in general, you're just kind of reshifting the drift of these two objects when you move to the right, the new one. So that's exactly this new, right? And let me show you, right? Suppose that you cancel the Brownian motion component. You don't care for this. When sigma equal to 0, then what does this equation become? It becomes r minus gamma lambda tilde equals to mu, or lambda tilde is mu minus r over gamma. That's exactly the same as your market price of risk in the other case, right? So the structure is exactly the same, yes, as before, except what's the difference? The difference here, we need to be more careful. Theta can be anything. But lambda tilde must be non-negative. Why? Because it's the rate of the Poisson process. A rate cannot be a negative number, right? You don't have negative rate. So when you solve for this equation, right, it's not just any good old equation. It's an equation where you require one of your solutions to be non-negative. But otherwise, right, the structure is very similar. For example, here actually you don't have to worry too much because, as I said, right, usually the rate of return for a stock is always higher than the risk-free rate. So here is non-negative kind of by market condition. But in general, right, when you put together the two sources of noise, then you have to be careful. Is it okay? Any question? So also to anticipate, right? Here you have one equation with two unknowns. So I think intuitively you see that for each theta and lambda tilde, you have one risk neutral probability, right? So how many risk neutral probabilities will we get under this model? How many risk neutral probabilities will we get under this model? Correct. Infinitely many. So this is exactly a case where you don't have a unique risk neutral probability. So the market is incomplete in this case, all right? That's not too much of a concern. The reason is we throw in two sources of noise with only one stock, okay? And that's a problem, but we're not really kind of modeling that part. But I just want to mention in passing that in terms of completeness, this model that we're looking at is incomplete. You want to throw in an extra stock to make it complete, okay? But that's fine, right? It's just because we had two sources of noise and one stock, okay? But now let's go back to right here, right? I was posing the question of what is the change of measure kernel. And I say it depends on what we want to happen under P tilde. So what do I want to happen under P tilde? What I want to happen under P tilde is that, right, of course, that W plus theta T, right, which is the W tilde, is a P tilde Brownian motion. And NT is a P tilde Poisson lambda tilde process. This is my wish list, right? This is what I want. This is what I want. So, right, going back to what Don was observing, these are the minimal condition, but absolutely, right, for my model to work, in order for my discounted stock price to be a martingale, then I need those extra things to happen. Okay. So this goes back to the old question we ask. What characterizes a Brownian motion? And also, right, what characterizes a Poisson process? And by asking this, we're not talking about the definition, okay? Definition is good, but in this context, as you see, if you drag in the definition at every point, checking that, this guy has independent increment, blah, 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 it will be a lot of work, especially when it comes to the distribution. Remember on your exam, I asked you to compute the expectation of WT under E tilde, right? Expectation tilde of WT. Right, I don't think any of you got it, but that's fine, right? But the problem, right, is you see that was just a expectation computation. If I ask you to compute the, the probability, imagine how much more cumbersome it is, right? So you have to think carefully about these kind of questions to see what the proper technique is. And the proper technique is the martingale categorization. Okay. And let me tell you what it is, right? And actually, you have seen this before. We claim something like this. WT is a Brownian motion if and only if e to the 1/2 minus 1/2 sigma square WT plus sigma WT is a martingale. Any sigma, right? And so let me throw in what works for the Poisson process too, and ask why. NT is a Poisson lambda process if and only if e to the gamma nt minus lambda t e to the gamma minus 1 is a martingale for any gamma. All right. So I hope that by now, somehow these two things are a little bit familiar to you. You have seen this not the first time. But besides the fact that this is true, right, and it will be the recipe for us to build the change of measure kernel, let's ask why. Why is this true? Right, intuitively, why do we have this? Where does it come from? Right, you were asked to, you recognize it's a martingale, right, a million times now. You're asked to do this on your homework of this week. But why is this true? why it goes both ways like this, right? So in other words, on the homework of this week, you're asked to prove this, but why it works this way too. Anyone? So the answer is, this is a generalization of moment generating function. Categorization. Okay. For example, let me ask you this. Suppose you know that expectation of e to sigma wt is equal to e to 1/2 sigma square. Oh, no one correct me. This is t, right? Sorry, not w. It's t, right? That's t. Is equal to this for any sigma. Suppose you know this. What can you conclude out of this? What does this imply? What does this imply? Well, what do you know about this? You know that this is the variance t, Cherry, right? The sigma is a little bit weird. The t in the usual moment generating function is right here. So that is the wrong sigma now. So that sigma square right here, all right? So yeah, right, this is the moment generating function. That's fine, right? It's easy to be confused. This is the moment generating function of the normal. So the conclusion is exactly that this allows you to conclude that this is normal. Okay. Same thing here. If you know that this is true for any gamma, then you can conclude that NT is Poisson lambda t. Okay. And again, right, you were asked to show that the moment generating function of Poisson is like this. So you see that by requiring this is a martingale, you're just doing a little bit more than that. So the martingale structure basically is this. That, and by the way, right, you see, so then it's not hard to see that this martingale is just this part divided by the moment generating function, right? It's just this part divided by the moment generating function. It's this part dividing by the moment generating function. That's all we do. So the martingale structure, right, allows you this. That, for example, with the Brownian motion, right, it allows you that you got expectation of e to a sigma wt minus ws. Condition is e to the 1/2 sigma square t minus s. Well, from here, you can draw two conclusions. One, that WT minus WS is independent of Fs. Why? Because there's no WS on the right-hand side. Second, WT minus WS is normal 0T minus S, because without the conditional, this is just the moment general function. And I hope you see, right, this is exactly from the martingale structure, because, right, this is just another way to write Does that make sense? So, right, calling this a martingale is just saying this, which allows you this, which exactly collapses to the moment check function. Right, same thing for the other guy. And so, right, you got two things. And by the way, right, this is normal. What am I saying here? There's nothing normal here, right? Poisson. Okay, like that. Okay. Any question? So what I just show you, right, is a more detailed explanation of the martingale characterization of Poisson process in bar motion, which is just a generalization of the moment general function technique. All right. And again, right, you see how martingale is deeply integrated into all these things we do. Because, right, let's not forget what we're doing. We're still looking for the change of measure kernel, right? We're looking for the change of measure kernel. And the change of measure kernel should be such that this is a tilde Brownian motion and this is a p tilde Poisson process, right? So go back to our wish list, right? So to say that we want ZT, right, so that W tilde, right, is a P tilde Brownian motion, and NT is a P tilde Poisson lambda tilde process, is the same as saying you want ZT so that e to the sigma W tilde T minus 1/2 sigma square T and e to the gamma, right, NT minus lambda tilde T e to gamma minus 1 are P tilde martingales. Okay. Is this clear? That I change, right? I change the question of ZT from a distribution question to a martingale question, to an expectation question, if you will, right? And I don't know how much you appreciate this from your probabilistic education, but working with expectation is always easier than working with distribution, and that's why. Okay. Any question on this? One last thing, all right, and then we'll take a break. One last thing is this, right? And you may wonder, okay, so what? I mean, sure, you may say that martingale make it easier, but I don't see how. How does that have anything to do with my ZT? And the answer is this, right? There's another martingale result that we did not say before, that now we say it. So a general lemma is like this, which is very useful. Let ZT, okay, be a P martingale with, expectation of ZT to be 1. So this is basically, just a change of measure kernel, right? Then, okay, let me say this, right? Define, right? Expectation tilde of X is expectation of ZT times X for X in FT, all right? Then the following happens. You may wonder, okay, this is true for the biggest sigma algebra, right? For the biggest one, because sigma algebra grows with time, right? Information grows with time. But what if I have something only in a smaller filtration? What happens? Well, the good news for you is it's just this. Very natural, but it works. Of course, right? Because this is true, it's a martingale. B, if you were to do conditional expectation, right, then you already know what happened, right? This is conditional expectation under the new one, right? Is conditional expectation under the O1 divided by this, right? So this we have used so many times, right, without ever saying why it's true. Now we will state it. And C is the most relevant one to us for this particular result, that you have a process, okay? So XT is a P tilde martingale if and only if XTZT is a P martingale. Okay. And so that exactly is what helps us to chase down what ZT is here. Because, right, we know that this is what we want to be martingale under the new probability. So this part C tells us that, okay, then just look for the kernel so that this times this is a martingale. And this times this is a martingale. And then you're good. And then you're good. Okay. Any question? So I think it's a good place to take a break here. Let's take a 10-minute break. I think we're on time. So let's go back at 10:50. All right. And then we'll continue with this proof and carry on with our change of measure kernel. All right, are we back? I'm going to continue. All right, so let's see where we left off, right? So we were kind of, this is where we, how to say this, right? This is a detailed characterization of what would happen when we do a change of measure kernel, all right? And this will help us to control the martingale properties that we want, all right? So if you will, this is like a change of measure kernel, change of kernel, yeah, change of measure kernel lemma, right? So let me say this. And I made a mistake here. This should not be tilde, right? It should just be E. So basically, the lemma is very, I think, straightforward or intuitive. It always relates, right? Because this is the new one, right? And this is the old one. And you define, this is your definition. So then it extends from this definition to what would happen, right, under the new one with what happened under the old one, right? New one, old one, new one, old one, right? New one, old one, okay? So let's go through the list and explain why things are true and kind of recall, right, how these are relevant to things that we have done before. For example, right, why is A true? A is very easy, right? Because basically you can use the definition. Of course, right, the point of A is that this random variable here is not in the big filtration, big sigma algebra, is in the smaller one. But how do we take advantage of that, right? How do we take advantage of that? That's easy. Well, you just take conditional expectation and then take expectation. Okay, because that's the law of like double expectation, right? After you take the expectation of conditional expectation, that goes back. But the advantage of this is because X is in FT, you can take it out. And you're left with, sorry, ZT, right? But we know that Z is a martingale. So therefore, like that, right? That's A. Okay. Where would you see this? Well, it's kind of unintentional, but in your midterm, all right? In your midterm one, I was asking you this. Right? I mean, I meant to ask this anyway. Okay. But because, I mean, the midterm was defined with the big T, right? And I did not kind of wanted to test you on like kind of this kind of property. But either way, I would expect that you would do something like this to begin with. In other words, you would use ZT, right? So in other words, so you would exactly do this. And that is because of A, right? So if you were to do this without showing anything, that would be fine, right? The point is to calculate this, but it was really a typo on my part. I meant to ask this, right? But you know, it's the same thing. like instead of doing big T like this, you do small t, but it's rigorously justified, right, by this property. Okay, so B actually is the more of a big deal kind of thing. B is saying that under the conditional, right, under the conditional expectation, then you can do this. And actually, I don't have to advertise for B, right? B we have used like all the time, right? B has been used all the time. So how do you show B? B is equivalent to saying this, right? Let me put a question mark here. B is equivalent to this. But why? Because ZT, right, is in FT, so you can bring it in. But why is this true? Why is this true? Remember, right, that you're not given a definition of conditional expectation. You're only given a definition for a change, a probability, right? So how do you infer from that to a conditional expectation? Okay. So that brings us back to the very definition of what conditional expectation is. So in other words, right, suppose that you have something like this. If conditional expectation of X based on something is equal to Y, what are you saying? What does that mean? This is something you should have learned from Professor Larson, but did he tell you what this is in general? Besides the properties, what is the definition of conditional expectation? So two things, right? That Y must be in FT itself. That means, right, that we know Y by observing the information up to time T. But more importantly, right, that for any, let's say, other random variable, let's say U in FT, then expectation of X times U is expectation of Y times U. These two things together guarantee that conditional expectation of X given FT is Y. Okay, so that allows that to happen. All right, so in this case, this is our Y right here. This is our Y. Okay, this is our Y. So what we want to show, right, because we're claiming, right, that this conditional expectation is equal to this. So what we want to show, right, is that for any U in FT, right, because we say conditional expectation of E tilde, right, that means that E tilde right, of this guy. So maybe let me just call it Y, okay? Times, oops, sorry. Expectation of Y times U is expectation of E tilde of X times U. Maybe my X is a little bit too confusing. Is equal to expectation of like that. Okay. Because right, this is my x in this case, and this is my y. So that's what I want to show. Okay. Now, so let's work on this side, right? So this is a question mark. Why is it true? Now, what happens here, right? What is this? Well, so actually, right, this will be, so e tilde of y times u, right? Because both of these are in ft, right? Both is in ft by part A, right? By part A, this will be expectation of zt times x. So that will be expectation of y times u times zt. Okay. But what is this, right? Now we can return what y is. Y is this, right? This is y. So that will be expectation of conditional expectation of zt times x given ft times u times zt, right? Which will become, right? Because then both of these are in ft. It will become expectation like that. Okay. Where I bring both of this inside. And now because it's the double expectation, right? It will become okay. Now I hope like all the notations do not confuse you yet. But right, I mean, I guess why both of these and things like that, right? Notice that we're just doing everything very carefully, just tracing, right? What it means to have e tilde and e, right? Going from e tilde to e, I pick up a zt. The rest is just writing down what I mean, what I call y, right here. This is y right here, right? This is my y, okay? So I just plug in what y is. Remembering that u, right, is in ft, and then use property of expectation. But the last step is this, right? The last step is, well, this is a change of measure kernel. This is a change of measure kernel, right? All this is in ft, in f big T. So in other words, this is nothing but my definition of zt ux, which exactly is the desired right-hand side. Okay, so I have shown that this is equal to this for any u and ft. So in other words, right, this is true. Is that okay? Any question on this? So right, this is the central, this is a central reason. There's no other way out of like, there's no easy way to show this besides using this as far as I can tell, right? So I rarely pull out this formula. It's not that pleasant to work with, but here that's the only way that works that I know. Okay. All right. So that kind of is the reason why we just want to remember this and work with it and not worry about too much about how to prove. Then the last detail is here, right? The last detail is here. So part C tells us that something is a martingale under the new measure if and only if the product with the kernel is a martingale under the old measure. Why is this true? Well, so let's check, right? So maybe let's go this way. So first of all, right, for s less than t, what we have is expectation of xt zt given fs is expectation of, is equal to xs times zs. All right. Now, what do we want? What we want, right? Somehow we want to show that this implies e tilde of xt given fs is equal to xs. But is that true? Well, that's exactly what part B was trying to tell us, right? Part B tells us how the conditional expectation moves from e tilde to e. So in other words, right, what we want here is that e tilde, right, of xt given fs should be equal to e of xt zt given fs divided by zs, right? But we know exactly that this guy is xs times zs. So we have that's equal to xs. Is that okay? Conversely, right, if we know this is true, then exactly because of the same formula, putting xs over here, then we know that this conditional expectation will be xs times zs, right? So conversely, if we know, right, that this is true, then because of exactly the same formula, we conclude that all right. Any question? So where did we see this? Where did we use this? Well, we did not use this directly, right? We did not use this directly, but we used it in the claim in the Gasanov theorem for the classical Black-Scholes model, where you say that if zt, right, is e to the minus theta times t minus wt, theta wt minus 1/2 theta squared t, then w tilde t, which is wt plus theta times t, is a p tilde Brownian motion, right? That's what we used, and you're asked to prove this, right, in your homework. But from the new point of view, right? So you used part B to do this, right? You use part B to do this. But if you were to use part C, how would you do it? If you use part C, what happens is it will ask you to show, right, because you claim that W tilde T, right? So this is exactly this. So we need to show that W tilde T times ZT is a P martingale. If you can show this, right? If you can show that W tilde T ZT is a P martingale, then you're done. Is it easier or harder than the other one? It's up to you, right? Remember, when you use part B to do this, there was some conditional expectation you need to calculate. What about this? How to show this is a martingale? Well, the difference is here you would use Ito formula to do this. You use Ito formula, okay? How so? In this way, that D, right, W tilde T ZT will be W tilde T dZT plus ZT dW tilde T plus the covariation like this, where the covariation is just a product. Is that okay? So basically I was applying Ito's formula. I hope this is familiar to you, right? Differentiating this times differentiate this times dW tilde, differentiate Z times this, and then you need to differentiate both and then do this. But because, right, so basically, right, it's like, so f of xy, right, is equal to x times y. F sub x is y, f sub y is x, and the cross derivative is 1, like that. There's no quadratic variation because f of xx is equal to 0. Is that okay? Apply to this. Well, but what do I know, right? What I know is this, that let me make sure that if it is a chat, I will see it. Okay. What I know, right, is that this part is a martingale. Why? Because ZT is a martingale, right? Let me do this. It's a P martingale. Okay. Is this a P martingale? Is this part a P martingale? Is this part a P martingale? So to answer that question, right, is W tilde a P martingale? Is W tilde a P martingale? Remember, P is our original physical probability. Okay. W tilde is W plus theta. So is W tilde T a P martingale? Yes, Don? No. Why? Because it has a drift part right here. It has a drift part, right? WT is a P martingale because it's a Brownian motion. But the drift exactly is what spoils it, right? Because WT has zero drift. So it's a martingale. But with this, then it's not. So in other words, right, this is not a P martingale. Okay. But never mind that. You know why? Because exactly right here is what corrects for that drift. Okay, let's see. How do we calculate this? Okay, what's dw tilde t? Dw tilde t is theta dt plus dwt. Okay, what about dzt? Well, this is zt right here, right? So I hope it's no surprise that dzt is minus theta zt dt, minus theta zt dwt. Because this is the solution. So this is dzt. Okay. So you see that dw tilde t dzt is minus theta zt dwt. Minus theta zt dt. Is it okay? Because this times this is dt, this times this is 0. All right. So let's look at these two terms again. So zt dw tilde t plus the covariation okay. So see, together, these two together will make you a P martingale. And so together, you see that this is a P martingale, not a P martingale, but after you compensate for the drift here, it becomes a P martingale. So together, this times this is a P martingale. Okay. And that concludes that W tilde T then is a P tilde martingale from part C. Okay. All this is, I understand, is can be a little bit complicated, all right, when you first are exposed to it. But you know, just kind of unwind this on your own at home and try to see. Basically, is all the pieces of the puzzle fits into the right block, all right? Trust me on that. It's just like keeping the block straight and what plugs into which part, that kind of thing. And then, you know, using the right formula. But all in all, right? I mean, I was showing you a Ito formula approach to verifying that W tilde is a Brownian motion rather than the expectation approach that you did before in your homework. Any question on this? Okay. So now let's go back to our question, right? Our question before we get into all of these right here. So now you want this to be a P tilde martingale, and this to be a p tilde martingale, right? So forget this for now, right? We know how to handle this because that's just the that's just the that's just this change of measure kernel. So we know how to handle the W piece. So, right, so let's pose our question again, right? So we want e to the lambda tilde nt, right, minus, sorry, e to the gamma nt minus lambda tilde t, e to the gamma minus 1, right, times zt to be a p martingale. What zt can we choose? Is that clear? This is what we want now. Okay, this is what we want now. What zt can we choose? Is this clear? All right. Now, this is a p martingale, right? So under p, so what kind of process? What process is nt under p? What process is nt under p? What process is nt under p? Nt is a Poisson lambda process, right? Nt is a Poisson lambda process. So basically, you know what kind of you expect, right? So that means you expect that e to the gamma nt minus lambda tilde t e to the gamma minus 1 times zt to be e to the gamma nt minus lambda t e to the gamma minus 1. 1 second. Sorry, I'm missing something here. Give me a moment. It's not that easy. Let me go back. Let me just give you the result and maybe explain it. It turns out that in this case, if we use zt to be e to the lambda minus lambda tilde times t divided by lambda times lambda tilde over lambda raised to nt, okay? Then we have the result that this right here will be a p martingale. Okay. So this is the change of measure kernel that we want for the Poisson process. All right. So to recap, for a Brownian motion, right, to change to W tilde, which is WT plus theta times T, then the change of measure kernel is e to the minus theta WT minus 1/2 theta squared times T. For a Poisson process lambda, to change to a Poisson process lambda tilde, then the change of measure kernel, let me call this Z1. Z2 is this guy right here. E to the lambda minus lambda tilde times T lambda tilde over lambda raised to NT. Okay. So I will try to give you a more intuitive way on why this happens, okay, next time. But for now, let me say this, right? If you want to change together, then you just use ZT to be the product of the two. Okay, and you just use this ZT to be the product of the two. So I guess maybe there's something for you to kind of explore at home. So two things, right? We need to verify. So one, right, that the Z2T is a P martingale. This process right here is a P martingale. And two, that when you multiply with this, right, it's also a martingale. So you need to we need to verify both. All right. So I'll left this as homework for you to do, or maybe review session problem. Okay. Any question on this? All right. So the goal, right, or the point is that we have shown you what the version for the change of measure kernel is for a jump process. And for when you have both together, then you just use the product of the kernels as a change of measure kernel. Now, so conclusion, right, is that we know how to change measure from the physical model to the risk neutral model. Okay. So what about pricing? What about pricing? Okay. In other words, suppose that now I have a co-option on this. What is V0? What is V0? Well, so for one thing, the pricing equation stays the same. In other words, V0 is still this, okay? Which is equal to this. Except the ST has now changed, right? The ST now is no longer the Black-Scholes model, but the ST now becomes S0 e to the R minus 1/2 sigma squared times T plus sigma W tilde T, right? And then you have the component, oh, I'm sorry, right? There's a lambda tilde too. So you have the R minus lambda tilde, right? Let me write down here. It's just a bunch of things to write. R minus 1/2 sigma square, that takes care of this. And then I need to take care of this. So minus lambda tilde times gamma, that times T. Sigma W tilde T, that takes care of this. And then you still have the Poisson, which, if you remember, is going to be NT times the log 1 plus gamma. This whole caboodle minus K plus. Okay, so that's what that is. In other words, right, that before, right, with Black-Scholes, because gamma is equal to 0, you have this and you have this. So if gamma equal to 0, this goes back to Black-Scholes. If you introduce the Poisson component, then this becomes your pricing equation where, right, W tilde T is a normal random variable, right? Where W tilde T is a normal random variable. NT is a Poisson random variable with rate lambda tilde. But, okay, if you want to get a closed form expression for this like Black-Scholes, there's no such thing. There is no closed form expression for this one. Why? Because you have the Poisson component here, right? So no nice closed form expression. And starting from here, right, you start to see that the power of explicit calculation starts to reduce and the power of simulation start to increase. In other words, if you want to know what V0 is, even with a call option, if you don't give me a computer, I don't know what to do. This is all I can do, okay? And so you see that I think starting from last week's review session, right, you start to have to simulate a Poisson process, a Poisson random variable, and simulate a normal random variable for pricing purposes. Is that okay? So that, like, the moment you increase your complexity a little bit, then you're outside of a Black-Scholes realm. I mean, there is something you can write down for this, okay? But I just don't want to get there. It's messy and there's nothing nice. So I'll just stop here and say, right, simulation is a reasonable answer, right? Yeah. In other words, if you want to get it, just try to do simulation until you see conversions, okay? So this wraps up what I want to present today. The last thing I want to talk about, or what I want to talk about in the next 5 minutes is, the next time. So we're almost done with jump model process. This is all I want to tell you about jump model process. But next time, what I want to discuss is the extension of the model to compound to general jump. Size. Okay. So what happens is before, right? NT only jumps by 1. So I think it was Meet that asked, right, that what if we want different jumps? Do we add different Poisson processes? And that's exactly the right way, but the right thinking. But generally, we want to do something like compound Poisson process. And so it's this compound Poisson process that I want to introduce. So basically, we will introduce a random jump size as being random, okay, once you jump. And so once you introduce this, you know what the procedure is. You have to revisit the whole thing and ask, okay, so what's the change of measure kernel? How do I change it? What's the risk neutral probability? All those kind of things. But it will not take long once we know what to do with Poisson process. And then the next thing I want to kind of mention is the approach of the PDE, right? Except that here there's no PDE, but it's something called partial differential difference equation. And the reason is when you look at your stock, you have two components. You have the Brine motion, which cause a second derivative and which would cause a partial differential part. But the Poisson process is not continuous. So what it does is it causes your stock price to jump. So it also causes your option price to jump. So what happens is your option price will behave with a jump component. And when you translate that to the differential equation language, it's not a differential, but it will be a difference, okay? Difference equation. So we'll mention that. Again, very, very abstract, because all we can do is to write down that equation. If you want to solve it, then you want to use some numerical approach, right? And if you get anywhere close to this kind of thing in your numerical 2 class, then that'll be good. Otherwise, it's just some kind of mention of this is an equation that you can learn how to solve using some numerical approach, but nothing that we can do like concretely in this class. Anyway, it's good for you to kind of see that thing a little bit. All right, so I think that's enough for today. I will answer any question you have. Otherwise, see you next time.
Hello, Professor. On the Google Finance, the volatility of the strike price over in the 100 in the 1800 and 2000, this interval are 0.
What are you talking about?
In the Google Finance, of many stocks are 0.
What is 0?
Volatility on the Google Finance website.
You're not asked to use that. You're asked to solve for the implied volatility. Do you understand? You're not asked to use it.
Yes.
You're asked to solve for it. So let's see, it's June 18, right?
Yes.
And where's the range? 1,800 something, right? I don't think so. First of all, the implied velocity is right here. I don't think there are zeros.
But in my website it's there zero.
In your what?
In my in my computer it shows zero.
All right. So that's the difference between real life and non-real life. Okay. I'm pretty sure you looked it up in sometime in China when the market's not open.
Oh, okay.
But again, right? The point is
Okay, and
the point is
okay, and let me take a screenshot of your website for these volatilities.
but I'm not asking you to use these numbers. You're supposed
Yes, but I should compare.
Oh, okay.
But I should compare.
I see. Yes. Yes.
Mm. And could you please let me see more?
Sure. You can access this right now, right? You can. I mean, there's nothing secret about what I'm saying. You can just go to your website too.
Okay. Okay. Okay, I have download. I have saved it. Thank you.
Mm-hmm.
And bye.
Okay. Bye. Any? Yeah.
Hi, I have just a really quick question because I realized I talked to Dawn about this question as well.
Mhm.
And I think like both initially I had used the last price
Yeah.
and then that's not correct, right? Am I supposed to, for the call price, is it the average between the bid and ask price, or are we using the last price as the
You
market
should
price?
use the average of bid ask because again, right? I think these are really real quantities that you should look up online, you know, like what they mean, right? And if you look up last price online, you see that last price is the price where it's last sold. Which,
Oh, okay.
which again, right, it's very interesting. This is finance, has nothing to do with math. They say that for things that actively traded, like stock, then these are pretty close. But you see, these are not close at all. Why? Because it could have been a couple of days ago that this is sold.
Is this last price, does it correspond to the last trade date? Is that why? Like some of them are really far off?
Exactly, right? You see, yeah, last trade date. Yeah, exactly. You see, wow, you're right? You see, someone bought it in 2025 months ago. If you use this, it's nonsense right now, right? So that's why the bid-ask spread, right, is what the market is willing to do it right now. It's live. Does that make sense?
Yeah, I see.
Yeah, and then you see some of them are a little bit more active, right? It also, but I think if you use the last ones in the between, you're not too far off, Sherry, right? Because I think a lot of them were actively traded. That's why I give you that range, you see?
Yeah.
So actually, if you were to use it, I don't think you move too far away from your graph. You see?
Yeah.
So I think it's not much of a danger. But if you were to use something like up here, right, then that was last traded in 2020s. And that's nonsense. But here, I think like they were just traded like, you know, recently. So they're more reasonable. But still, I guess, yeah, for that matters, right? I mean, the mid price is the most reasonable one to use.
Okay. Yeah, thank you. I
Sure.
also wanted to like just making sure you still have your office hours tomorrow, right? Like
Yeah,
there's
yeah,
still
always. Sure.
Okay. Yeah, I think I want to go over because like there was that I think question number 4, I couldn't understand it even when we did it in the lecture, but then I just like skipped over a part of it when solving for the expectation of like e to the power of wt and then times another wt in there. And then I just remember not being able to do that expectation in the lecture, and then I couldn't do it on the midterm. So I wanted to like maybe after I try it again today to go over it with you tomorrow, if that's okay.
Yeah. But so I posted the solution, right? Do you?
Yeah, I don't really understand even after the solution, but it's like
No, it's fine. But let's say B is a trick. There's a trick. There's a technique to do so. If you were to try to do it directly, it's super painful actually.
oh okay,
It's not that painful, but it's not that nice to deal with, and that's why the trick is to view it as a derivative. I'll be happy to explain to you tomorrow in office hours.
okay.
You can try your approach, right? And I think it's better if you try your approach and you fail or you know found it the hard way, then I think you will appreciate what I do more. Yeah, but I'll explain to you more tomorrow. Yeah.
Okay, thank you so much.
Sure.
Bye.
See you. Do you have any question, Kashif?